Okay, now we're looking at page 230, activity 13C, Kirchhoff's laws. Question 1 is a series of diagrams with currents flowing into and out of the junctions. In the first example, A, you have 2.6 amps flowing in and 1.7 amps flowing out, along with the current, the unknown current value I. So simply subtracting those two values will give you the value for I. In this case it's 0.9 amps. For number 2, part B, we are looking at all the current going in, so that's 2 plus 2.4. Applying Kirchhoff's first law, that must equal all the current flowing out, which is 3.1 amps plus the unknown value I. Rearranging and solving for I, 4.4 minus 3.1 will give us it, and that's 1.3 amps. Part C, in this case, we have 3 currents flowing out and just 1 current going in. One current going in is 4.5. That must be equal to the sum of the 3 currents going out, 1.2 plus 0.7 plus the unknown value I. So solving for I, we get 4.5 minus 1.9, which gives us 2.6 amps. Part D, you have 2 currents flowing in and just the 1 current flowing out, which is the 0.8 amps. The 2 currents flowing in involves the unknown plus the 0.15. So rearranging, you get 0.65 amps. Question 2, you have a diagram with a couple of cells, one unknown, 2 resistors. The first question is just ask you to find the current I in the 2 ohm resistor. Now if you look at the junction A, you can see that there are 2 currents flowing out, 1 current flowing in, with 4 amps, and so applying Kirchhoff's first law, the sum of the current going into the junction must equal the sum of the current flowing out. We can find that I equals 1 amp. That's the one flowing through the 2 ohm resistor. Part B, use Kirchhoff's voltage law to calculate the voltage V. Now, looking at that diagram, they've given you a dotted loop circle indicating that you should perhaps go that way. It doesn't matter actually which way you go. We'll just follow their direction. Okay, so we're going to move anti-clockwise with that dotted green arrow. And we can start at junction A. Doesn't really matter where you start as long as you finish at the same spot. Applying Kirchhoff's second law, starting at point A and moving anti-clockwise, we're going to go through the cell, which is worth 1 volt. So we write down 1, a positive 1, because we're going from the negative to the positive terminal of that cell. Then we're going to subtract a drop because we're going across the 2 ohm resistor. Now we know the value of the current, it's 1, so the value of the drop is I times R, 1 times 2. And then we go down past junction B, encountering nothing until we get to the unknown cell V. Since we're going through it backwards from the plus to the minus, we're going to drop that voltage. That's why you have to minus V. The last thing is you come to the 3 ohm resistor, and because we're going backwards against the current direction of 3 amps, we are going to actually add that voltage. That's why there's a plus here. So we're adding 3 times 3, I times R. I is the current, 3 amps, and this value 3 is the resistance, 3 ohms. Now all those will sum, that's the entire thing, because after that there's nothing. We go back to point A. That must all equal 0. Okay, that's the voltage law applied. Simplifying that down, 1 minus 2 minus V plus 9 equals 0. Rearranging and solving for V, you get 8 volts. Now looking at question 3, the first question asks you to find the value of the current through resistor R2. You can look at junction C and apply the first law. The first law is current into any junction must equal the current out. So they've shown us 0.75 going in to junction C from both directions, so it's 0.75 plus 0.75. And that must equal the current through that R2 resistor. You can see it will flow around past D, through E, across to F. And that value is 1.5 amps, of course. Part B. By considering the potential differences around the loop, A, B, C, F, A, calculate the resistance R1. So we're going to apply the second law. Whenever it says that, consider the potential differences around the loop, it means apply the second law. The sum of the voltages in that loop must equal 0. Now we'll choose to start at point A and move clockwise. It doesn't really matter where you start and which direction, as long as you consistently move around that entire loop and come back to the starting point again. So at point A, nothing's happening until we get to the 3 volts battery, in fact, 2 cells in series. And we therefore gain 3 volts because we move from the negative to the positive terminal as we move from A to B. So it's a positive 3 volts. Then we go along, nothing's happening until we get to junction C and turn down through a 1.5 volt cell backwards. That means we drop 1.5 volts. That takes us to junction F, and then we go across to A again. Now we're crossing a resistor R1 with the current, so we're going to drop voltage. We're dropping the current times that resistance value, I times R. That's the unknown which we're going to solve for. Now these voltages all sum to 0. That's the law. So we rearrange, solve for R1, it turns out to be 2 ohms. Okay, part C. What would be the reading on the voltmeter across R2? In this case, the easiest way to do this is to look at loop FCDE, which contains R2, and apply the second law. Now we have the cell. If we start with the cell, start at, say, junction F and move across that cell with the current, we gain 1.5 volts. Then we come around, nothing's happening until we get back to the resistor R2. There'll be a voltage drop in that resistor, which will be the same reading as the voltmeter across it, of course. We'll just call that V subscript R2. And nothing else, so we're back to F after that. Very simple equation, it equals 0. Therefore, of course, that must be 1.5 volts, the reading of the voltmeter. The last one, part D, to which point E or F should the positive terminal of the voltmeter be connected? Explain your answer. Well, since we know the current is flowing from E to F, we need to connect the positive terminal at point E. That's because you always connect to the higher potential end. The positive terminal means it is higher, and the negative means it is lower. And that's the reason.